Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I will share my answers and scoring guidelines for the 2026 released free response questions. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Check out the links in the video description area, which include the link to the 2026 released free response questions and the link to my version of the scoring guidelines. Now, the official scoring guidelines will be available on the College Board's website in the fall. So my scoring guidelines are my best guesses regarding the answers to each question and the number of points that are assigned to each part of each question. Okay, let's get started. This is question 1. Question 1 is worth 10 points, and it begins as follows. A student performs a calorimetry experiment with potassium chloride. Consider the potassium ion in potassium chloride. Write the complete ground state electron configuration for the potassium ion K+. So on the periodic table, we can see that potassium, the atom, has a total of 19 electrons, and then the potassium +1 ion will have lost 1 electron, so it will have 18 electrons. The electron configuration begins with 1s2, followed by 2s2 and 2p6, and then we have 3s2, 3p6, and then finally 4s1 if we were writing the electron configuration for the potassium atom. But since the potassium ion +1 has lost that outer shell electron, the correct answer would be 1s2, 2s2, 2p6, 3s2, and 3p6. Now, at the AP reading, it is possible that they will also accept the noble gas abbreviated version of this electron configuration, in which 1s2, 2s2, 2p6 is replaced with the element neon in brackets. And if that is accepted, then neon 3s2, 3p6 would be an alternate answer for this first point. Let's move on to the second point, which is, which has the larger radius, the potassium ion or the potassium atom? Explain your reasoning using principles of atomic structure. So the difference between these two electron configurations is the presence of an occupied electron in the 4s orbital. So what I said for that second point is the following. The potassium atom has the larger radius because the highest occupied electron shell, energy level 4, of the potassium atom is at a greater average distance from the nucleus than the highest occupied electron shell, energy level 3, of the potassium ion. So that's the second point. Now let's move on to the third point in question 1. And it has to do with this calorimetry experiment. It says a student performs an experiment to determine the enthalpy of solution of KCl. The student places water in a calorimeter, measures the initial temperature, adds solid potassium chloride, and stirs until the potassium chloride dissolves completely. The temperature is continuously monitored during the experiment, and data from the experiment are given in the following table. So in addition to the mass of water and the mass of the solid potassium chloride, we see the initial temperature of the water before the potassium chloride is added is 24.5 degrees Celsius. And then the final temperature of the solution, once all of the potassium chloride dissolves completely, is 21.1 degrees Celsius. So for the third point, describe how the student can use the temperature readings during the experiment to determine when the dissolution is complete. Now, the temperature decreases as the potassium chloride is dissolved, so we're looking for the lowest possible temperature. What is the minimum temperature? So what I said for that third point is the following. The dissolution of potassium chloride should be complete when the temperature of the solution remains constant over time. So if the temperature is still dropping, that means the dissolution is still occurring. So if the temperature is still decreasing, then the dissolution process is still occurring. But once the temperature remains constant over time, the dissolution of potassium chloride should be complete. Now let's move on to the fourth point. This has to do with calculating the magnitude of thermal energy, Q, in joules that was transferred during the dissolution. And we are given that the specific heat capacity of the solution is 3.95 joules per gram degree Celsius. So we will go ahead and set up the Q equals M times C times delta T. And the M is going to be the mass of the entire solution. That would be the water, 97.5 grams, plus the mass of the solute, the potassium chloride, 6.80 grams. And then we have that specific heat capacity that we were given. And the change in temperature would be 21.1 minus 24.5. Now, what we're looking for here in our answer is the absolute value, because it says calculate the magnitude of the thermal energy. So I'm not worried about the sign of Q. Even though it says negative 1400 for the amount of Q, the magnitude can be written as 1400 joules. So most likely the AP readers will ignore any signs in this answer. So 1400 joules, and that is the amount of thermal energy that is absorbed. The dissolution of potassium chloride is endothermic because heat is absorbed. If heat were released, then the temperature of the solution would increase. But since the temperature of the solution decreases, then this is an endothermic process. So we expect the sign of delta H for the dissolution of KCl to be a positive value. All right, well, that's point 4. Let's move on to point 5. Now we have to calculate the molar enthalpy of solution, and that would be in units of kilojoules per mole. So 1400 joules divided by 1,000 will be 1.4 kilojoules. So that's 1.4 kilojoules divided by the number of moles that we were given, which is 0.0912 moles of KCl. And so when we do that math, the positive delta H value works out to be 15 if we round off to two significant figures. So positive 15 kilojoules per mole would be for point 5. Now moving on to point 6. It says the calorimeter is not perfectly insulated. Would this cause the magnitude of delta H of solution, calculated in part C, Roman numeral 2, to be greater than, less than, or equal to the accepted value? Justify your answer. So now there's going to be heat exchange between the calorimeter and the surroundings. So for my answer to this question, I said less than. And my justification is the following. If the calorimeter is not perfectly insulated, heat would be exchanged between the laboratory and the solution, resulting in a higher final temperature of the solution. So the final temperature of the solution is 21.1 degrees Celsius, but if the laboratory temperature is warmer than that, and there is heat exchanged between the laboratory and the calorimeter, then that final temperature of the solution would be higher than 21.1 degrees Celsius. And this would result in values of delta T, the Q of the solution, and the delta H of solution that are smaller in magnitude than the accepted value. So that is my answer to point 6. Let's move on to point 7 of this question. It says, the student performs a second experiment using the same mass of water, but 6.80 grams of rubidium chloride instead of 6.80 grams of potassium chloride. The magnitude of the molar enthalpy of solution, delta H, of rubidium chloride is approximately equal to that of potassium chloride. So the question asks, is the magnitude of delta T in the rubidium chloride experiment greater than, less than, or equal to that in the potassium chloride experiment? Justify your answer. Assume that the specific heat capacities of the solutions are equal. So the main difference here is going to be the number of moles of the solid that was added to the water. So I said less than, and my justification is the following. A sample of 6.80 grams of solid rubidium chloride contains fewer moles than 6.80 grams of solid potassium chloride, because the molar mass of rubidium chloride is greater than that of potassium chloride. And if fewer moles of solute is dissolved in water, then the values of the Q of the solution and the delta T in the rubidium chloride experiment would be smaller magnitude than those in the potassium chloride experiment. All right, well, that's my answer to point 7. Let's move on to point 8 of this question. We have to write the net ionic equation for the dissolution of rubidium chloride in pure water. And that would be solid rubidium chloride on the left, and the aqueous ions, rubidium +1 and chlorine -1, on the right side of the equation. Now, the phases of matter are not required, but if you do use phases of matter, they should be correct, with solid rubidium chloride on the left and the aqueous ions on the right. So, for the next point, we are given the KSP value for rubidium chloride. It is 57 at 20 degrees Celsius. And we have to calculate the molar solubility of rubidium chloride in a saturated solution at 20 degrees Celsius. Show the work that leads to your answer. So I wrote the KSP expression for rubidium chloride, and the solubility would be S times S equals S squared. And that means that the molar solubility of rubidium chloride would equal the square root of 57, which is 7.5 molar. Now, the final point in this question, it says a second saturated solution is prepared by dissolving rubidium chloride in 1 molar potassium chloride at 20 degrees Celsius instead of pure water. This is the common ion effect. So will the molar solubility of rubidium chloride in 1 molar potassium chloride be greater than, less than, or equal to the molar solubility calculated in part FII? Justify your answer. So what's happening here with the common ion effect is that the solubility of rubidium chloride should be decreased in the presence of a common ion. So this is what I said, less than, because the potassium chloride solution already contains a common ion, the chloride ion, the molar solubility of rubidium chloride will be decreased. All right, well, those are my answers and explanations to all 10 points of question 1. Let's go ahead and move on to question 2, which is also a 10-point question. In question 2, it says, answer the following questions about the chromate ion CrO4 2- and the dichromate ion Cr2O7 2-. The bonds between chromium and oxygen in the chromate ion can be represented as covalent bonds, and one possible Lewis diagram for the chromate ion is shown in Figure 1. Based on VSEPR theory, predict the molecular geometry of the chromate ion. And so that would be tetrahedral geometry. So that's the first point. Now for the second point, it says on Figure 2, draw a complete Lewis diagram for a resonance structure of the chromate ion that results in a formal charge of 0 on 2 of the oxygen atoms and a formal charge of -1 on the other 2 oxygen atoms. Your diagram should contain the same number of valence electrons as in Figure 1. So in Figure 1, we have a total of 32 electrons. We're going to use 32 electrons for the diagram in Figure 2. All we're going to do is change 2 of the single bonded oxygens into double bonds. And so what that will do is put a formal charge of 0 on those double bonded oxygens. So that is the correct answer for this next part of the question for point 2. Let's go ahead and move on to point 3. Now we have to write a balanced net ionic equation for the reaction between the chromate ion and a strong acid. So that would be the chromate ion plus H plus to represent a strong acid, and then the products are the dichromate ion and water. So we'll write the dichromate ion Cr2O7 2- on the other side of the equation, and water. Now I'm using phases of matter, so I've got aqueous for all of those ions, and then liquid for water. Again, you don't have to include phases of matter to earn the point, but if you do use phases of matter, they should be correct. Now I'm not quite done. I have to put a 2 in front of the chromate ion on the left so I can get 2 chromium atoms to balance the equation. And then I also need 2 hydrogen atoms on the left side of the equation. So I'll put a 2 in front of the H+. So now I have a balanced equation, a net ionic equation. This is not only balanced in terms of atoms, it's also balanced in terms of the overall charge. So we have an overall charge of -2 on both the left side and the right side of the equation. Now there is an alternate acceptable answer to this equation. If you write H+ for the strong acid, then this is correct, but some students would prefer to write the hydronium ion to represent a strong acid. So if I show the hydronium ion as H3O+, I would need to add 2 more water molecules on the other side of the equation. So with this alternate acceptable answer, I have 2 H3O+ on the left, and I have 3 H2O on the right. All right, well, that's for point 3. Let's go ahead and move on to point 4. So is the reaction a redox reaction? Justify your answer based on the oxidation number of Cr. Now, the chromate ion on the left has an oxidation number of +6 for chromium. And the dichromate ion on the right side of the equation, the oxidation number of chromium is also +6. So my answer to this question is no, this reaction is not a redox reaction because the oxidation number of chromium does not change during the reaction. The oxidation number of chromium is +6 in both the reactant, the chromate ion, and the product, the dichromate ion. Let's move on to point 5 of this question. And so this is actually point 5 and point 6. Now, I'm not sure if this is correct, but I have assigned 2 points to part C of this question. 1 point for the calculated value of delta G, and then 1 point for determining whether the reaction represented by equation 2 is thermodynamically favorable or not. So here's my calculation of delta G. I'm using delta G equals -N times F times the cell potential. So that would be the number of moles of electrons. There's 6 moles of electrons in equation 2 for every 1 mole of reaction. And then the Faraday constant, 96,485 coulombs for every 1 mole of electrons. And then I have my cell potential is -1.32 volts, but a volt is equal to a joule divided by a coulomb. And so at this point, I have an answer in joules. I'm going to convert to kilojoules. So when I finish off this calculation by dividing by 1,000 to convert from joules to kilojoules, this is what I got on my calculator. I got positive 764 kilojoules per mole of reaction. And then based on that positive delta G value, I said the reaction is thermodynamically unfavorable under standard conditions because delta G is positive. So again, I assigned 2 points to part C of that question. I don't know. We'll see if the official College Board scoring guidelines agree with me or not. Now, moving on to what I'm calling point 7 of this question. It says, calculate the number of grams of solid chromium that could be plated onto the surface of a steel rod when 15 amps of current is applied for 3,250 seconds. So I'm first going to convert from seconds to coulombs because 15 amps is also 15 coulombs per second. Then I will use the Faraday constant. I'm going from coulombs to moles of electrons. So it's going to be 1 mole of electrons for every 96,485 coulombs. Then it would be from moles of electrons to moles of chromium. So there's 1 mole of chromium for every 6 moles of electrons. And then finally, from the periodic table, there's 52 grams of chromium for every 1 mole of chromium. So there's my unrounded answer when I did that math. And then my rounded answer based on 3 significant figures is 4.38 grams of chromium. So it is possible that the part C is worth 1 point, and then part D is worth 2 points. So points 5, 6, and 7 would be split up among parts C and D of this question. Let's go ahead and move on to point 8. And what we see is a graph of concentration of the dichromate ion versus time in minutes. Explain how the data in figure 3 support the conclusion that the reaction is first order with respect to the dichromate ion. So what I did was I looked for when 0.5 changes to half of that value. So half of 0.5 is 0.25. It took 20 minutes for the concentration of the dichromate ion to decrease from 0.5 to 0.25. And then half of 0.25 is 0.125, which looks like it takes another 20 minutes. So my answer to this question is the following. The data in figure 3 show that the disappearance of the dichromate ion has a constant half-life, which indicates that the reaction is first order with respect to the dichromate ion. And again, the value of the dichromate ion, the concentration is reduced by half every 20 minutes. All right, moving on to point 9 of this question. We are given a plot of natural log of the concentration of the dichromate ion versus time, and we have to calculate the value of the rate constant. Now, when you're looking at a linear plot of natural log of concentration versus time, the absolute value of the slope of the line is equal to the rate constant k. So I'm going to do the difference in the y-axis divided by the difference in the x-axis. And so if I pick this particular point that is at negative 0.8 on the y-axis, and then I go to this point, which is negative 1 on the y-axis, that's a difference of negative 0.2 on the y-axis. And that was between 3 minutes and 9 minutes. That would be a difference of 6 minutes on the x-axis. So what I'm going to do is calculate the absolute value of the slope. And that would be 0.2 divided by 6, which is going to give me a value of 0.033 with units of inverse minutes. So 0.33 is my value of the rate constant with units of inverse minutes. Now, there is another possible acceptable answer to this point, and that would be not based on this graph, but based on the knowledge that the half-life is 20 minutes. So if you look at the half-life equation on the equation sheet, 0.693 divided by the rate constant k equals the half-life. So 0.693 divided by the half-life equals the rate constant k. So that would be 0.693 divided by 20 minutes, or 0.035 minutes, so inverse minutes. So it is possible at the AP reading that they will accept either 0.033 inverse minutes or 0.035 inverse minutes for the value of the rate constant k. And now there's one more point in question 2, and we have to draw a line. We have to draw the plot of natural log of the dichromate ion versus time when we start with an initial concentration of 0.25. Now that's 0.25 molar, and the natural log of 0.25 molar would be negative 1.4. So what I'm going to do is continue a line that has the same slope as the previous experiment. So I'm going to go down by 0.2 and then over by 6 minutes. Down by 0.2, over by 6 minutes, down by 0.2, over by 6 minutes. So this is the line that I drew, which is parallel to the previous line, but it starts at negative 1.4 on the y-axis. So again, that would be the 10th point. All right, well, these are my answers and explanations for all 10 points of question 2. So now let's go ahead and take a look at question 3, which is also worth 10 points. In question 3, it says nitrous acid, HNO2, is a weak acid that ionizes according to equation 1. So in the first part of this question, we need to identify a conjugate acid-base pair in the equation. Be sure to clearly label which is the acid and which is the base. So the first reactant listed in the equation is HNO2, and that is an acid. It's a proton donor. And the conjugate base would be the ion on the other side of the equation. That would be NO2 minus. So one possible answer to part A is that HNO2 is an acid, and NO2 minus is its conjugate base. Well, if HNO2 is behaving as a proton donor, that means that the other reactant, water, is going to be behaving as a base or a proton acceptor. And so if water is behaving as a base, then its conjugate acid would be on the other side of the equation. That's the hydronium ion. So another possible acceptable answer for a conjugate acid-base pair would be H2O is a base, and H3O plus, or the hydronium ion, is its conjugate acid. All right, so that's two possible answers for point 1. Moving on to point 2. Calculate the value of the concentration of the hydronium ion in the solution, and we are given that the pH of this solution of nitrous acid is 2.09. So if I write the pH equation, pH equals the negative log of the hydronium ion concentration. Now we know the pH is 2.09, then 10 to the minus 2.09 will give me the concentration of the hydronium ion for this solution. So 10 to the minus 2.09, I get 8.1 times 10 to the negative 3 molar. So that would be my answer for point 2. Now, in point 3, we have to calculate the equilibrium concentration of HNO2. And so we have to show our work. I'm going to try two methods to calculate this value. Here's a rice table in which the initial concentration of the nitrous acid is 0.125 molar. I'm not worried about the concentration of water. And then, assuming that this reaction has not yet occurred, the initial concentration of the NO2 minus ion would be 0. And considering that in pure neutral water, the concentration of the hydronium ion would be 10 to the minus 7, I'm going to assume that the concentration of the hydronium ion is approximately 0. Now, it's going to be minus X for the HNO2, and then plus X and plus X for the two products. And at equilibrium, it would be 0.125 minus X and X and X. Now, in the previous problem, we calculated that the concentration of the hydronium ion is 8.1 times 10 to the negative 3 molar. So I can fill in the bottom of my rice table with concentration of NO2 minus, the same as the concentration of the hydronium ion, and 0.125 minus 8.1 times 10 to the negative 3, that gives me a value of 0.117. So that would be one way to show the work that leads to a concentration of 0.117 molar for HNO2 at equilibrium. Another possible setup would be, because we are given the Ka expression and the Ka value, then we can go ahead and just plug in everything we know except for the concentration of HNO2 at equilibrium. So in the numerator, that would be 8.1 times 10 to the negative 3 squared. In the denominator is the equilibrium concentration of HNO2, and I set that equal to the Ka of 5.6 times 10 to the negative 4. And when I do the math to solve for the concentration of HNO2, I get 0.117, which I might round that off to two significant figures. So either 0.117 or 0.12 molar. Again, these are different ways of solving for this particular point, point 3 in question 3. Let's go ahead and move on to point 4. Calculate the value of Ka at a different temperature at 333 Kelvin. Now, we were given the equilibrium concentration of HNO2, NO2 minus, and the hydronium ion. So all we have to do is plug in these three concentrations into the Ka expression. Now, when I do this math, I'm going to get a different value of Ka than what I have for 298 Kelvin. So when I do this math, I get 1.04 times 10 to the negative 3, and this is the Ka value at a higher temperature at 333 Kelvin. So our follow-up question, which is going to be point 5, would be related to Le Chatelier's principle. So is the reaction represented by equation 1 endothermic or exothermic? Justify your answer by comparing the Ka values at 298 Kelvin and 333 Kelvin. So because the Ka value has increased at this higher temperature, I said endothermic. So the value of Ka for HNO2 at the higher temperature, 333 Kelvin, is greater than the value of Ka at the lower temperature, 298 Kelvin. And that represents a shift toward the products. And so endothermic reactions will favor product formation at higher temperatures. So that's my justification for why I think that the Ka value increasing represents an endothermic reaction. We expect the Ka value to increase at a higher temperature for an endothermic reaction. Let's go ahead and move on to point 6 of this question. Now we have a titration. We have a titration curve, and part D, which is point 6, says identify the pH at the equivalence point. So I drew two roughly diagonal lines at the equivalence point, past the equivalence point, before the equivalence point, and so roughly halfway between these two diagonal lines would represent the pH at the equivalence point. So I'm going to estimate it's approximately pH 8. I'm also going to assume that at the AP reading they would provide guidelines for an acceptable range of pH values. So I'm assuming it would be approximately between pH 7 and 9, but I chose pH 8 for the pH at the equivalence point. Now on to point 7 of this question. Using figure 1, calculate the molarity of the nitrous acid in this solution. So we have a bottle and we have a concentration that is unknown of this nitrous acid, and the student titrates 35 milliliters of this solution of nitrous acid of unknown concentration. So we know the concentration of the sodium hydroxide is 0.16 molar. We know that the volume required to reach the equivalence point is 50 milliliters. So I wrote 0.0500 liters. I just divided by 1,000. So 50 divided by 1,000, that's my volume in liters. I multiplied by the molarity of the sodium hydroxide. There is a 1-to-1 mole ratio between the sodium hydroxide and the nitrous acid. And so I've gotten that calculation is 8 times 10 to the negative 3 mole of nitrous acid, and that 35 milliliter sample I'm dividing by the volume in liters. So 8 times 10 to the negative 3 divided by the volume of the nitrous acid in that bottle, and I got 0.0350 when I divided 35 by 1,000. So my molarity is 0.23 molar. Now, if you're watching this video and you said, Mr. Farabaugh, I did it a different way and I think I got the same answer, I'm going to go ahead and show you that different way involving molarity of acid times volume of acid equals molarity of base times volume of base. So we don't know the molarity of the acid, but we know the molarity of the base is 0.16 molar. The volume of the base required to reach the equivalence point is 50 milliliters or 0.05 liters. And then the volume of the unknown concentration of nitrous acid was 35 milliliters or 0.035 liters. So when I did that math, I got that same answer of 0.23 molar for the concentration or the molarity of my nitrous acid. Well, that's point 7. Let's go ahead and move on to point 8 of this question. Draw an X on the titration curve in figure 1 to represent a point in the titration where the concentration of nitrous acid is greater than the concentration of the conjugate base, NO2-. Well, we have to be before the half equivalence point for that to occur. So if the half equivalence point is at 25 milliliters, then for the concentration of HNO2 to be greater than NO2-, it should be before the half equivalence point, so anywhere on a point greater than or equal to 0 and less than 25 milliliters. So that would be one acceptable answer, but anywhere between 0 and 25 milliliters for your point X. All right, well, that would be point 8. Let's go ahead and move on to point 9 of this question. We have to calculate the value of K2 for a reaction in table 1. So we have the Ka, we have the Kw, and then we have a reaction for K2. So how would these two equations be combined to produce the equation represented with K2? We have to calculate the value of the equilibrium constant for equation 2. Now, the first thing I notice is that HNO2 is on the left, which is what we see in the Ka equation. So I'm not going to do anything with that first equation. I will leave it unchanged. Then I notice that the hydroxide ion is on the left in the equation that I'm looking for, but the hydroxide ion is actually on the right in the Kw equation. So that equation should be reversed. So what I will do is leave the first equation unchanged, reverse the second equation, and then I multiply those two K values together. So it's going to be Ka times 1 over Kw, and when I do that math, I will get 5.6 times 10 to the 10. So for 0.9, I get a K2 value of 5.6 times 10 to the 10. And now the last point of question 3 is a student makes the claim that methyl orange was the best choice for the indicator in this titration. Well, I need my acid-base indicator to change color at approximately pH 8 so that my indicator will change color at a pH that is near the equivalence point. So my answer to this question was I disagree. Methyl orange changes color during a pH range of 3.1 to 4.4, but that is before the equivalence point of the titration, which is at pH of 8. So I said I disagree. Now, this question did not ask me to choose the best indicator. It only asked me to agree or disagree with the student's claim that methyl orange was the best choice. So I said I disagree. Methyl orange is not the best choice. Again, because methyl orange would change color between a pH of 3 and 4, and that is before the location of the equivalence point of the titration, which is around pH 8. All right, well, those are all of the answers and explanations to question 3. Now let's move on to question 4, which is a shorter question that is only worth 4 points. In question 4, it says white phosphorus, which has the chemical formula P4, can decompose into P2 at elevated temperatures. A balanced chemical equation, the Kp expression, and Lewis diagrams for the chemical species involved in the reaction are given. Now, the first point, part A, it says the average bond length in P4 molecules is 221 picometers, whereas the average bond length in P2 molecules is 189 picometers. Explain why the average bond length in P4 is greater than the average bond length in P2. So what we are doing is we are comparing the single bonds in P4 molecules with the triple bonds in P2 molecules. So this is what I said for part A. The triple bond in the P2 molecule is stronger and shorter than the single bond in the P4 molecule. So that was for point 1. Let's go ahead and move on to points 2 and 3. And so in part B, a sample of P4 solid is placed in a sealed rigid container and heated to 1600 Kelvin, at which point the initial partial pressure of P4 gas is 0.470 atmospheres. Some of the P4 gas decomposes into P2 as the system reaches equilibrium. At equilibrium, the partial pressure of P2 is determined to be 0.630 atmospheres. And so the question is, calculate the value of the equilibrium constant, Kp, for the reaction at 1600 Kelvin. Now, I made a Rice table, and I'm calling this a 2-point question, where 1 point is to determine the equilibrium partial pressure of P4, and then the other is to actually calculate the value of the equilibrium constant Kp. So in my Rice table, I've got P4 as the reactant, and then P2 as the product. The initial partial pressure of P4 is 0.470 atmospheres. And since the reaction has not yet occurred, the initial partial pressure of P2 would be assumed to be 0. Now, because there's a coefficient of 1 and 2, I have minus x plus 2x. And then at equilibrium, I have 0.470 minus x and 2x. But they tell us that at equilibrium, the partial pressure of P2 is determined to be 0.630. And if 2x equals 0.630, that means that x would be half of that value. So 0.315 equals x. And if 0.470 minus x can now be calculated as 0.470 minus 0.315, then I think that the second point would be earned for determining the partial pressure of substance P4 at equilibrium. That's 0.155 atmospheres. And then the third point would be to set up the Kp expression and plug in 0.630 for the product partial pressure, and that would be squared, divided by the reactant partial pressure of 0.155. So when I did that math, I got 2.56 for my value of Kp for the reaction. So again, point 2, in my opinion, is to determine the partial pressure of P4 at equilibrium, and point 3 is to calculate the value of the equilibrium constant Kp. And then the last point of this question is based on thermodynamic favorability. The reaction is thermodynamically favorable under standard conditions, but only at temperatures above 1500 Kelvin. And a student claims that this reaction must be endothermic because it is favorable only at high temperatures. Do you agree or disagree? Justify your answer by using the delta S and the delta G for this reaction. So I said yes, I agree. For an endothermic reaction, the delta H is positive. And then for this reaction, the delta S is also positive because the number of moles of gas phase products is greater than the number of moles of gas phase reactants. So I've got a positive delta H and I've got a positive delta S, and given the equation delta G equals delta H minus T delta S, the reaction must have a delta G that is negative to be thermodynamically favorable. And if a reaction is favorable only at high temperatures, then both the delta H and the delta S would be positive. So that's my answer for the last point of question 4. So hopefully that all makes sense, because now let's go ahead and take a look at our next question, question 5, which is also a 4-point question. In question 5, we are given a Lewis diagram of CBr-Cl-F2. And part A asks, which of the bonds is the most polar? Justify your answer. So is it carbon-bromine, carbon-chlorine, or carbon-fluorine? Well, based on differences in electronegativity between the two atoms, it is the carbon-fluorine bond that is the most polar because it has the greatest difference in electronegativity between the two atoms. So that's the first point in question 5. Now, moving on to the second point, in a molecule of CBr-ClF2, there are different bond angles. The fluorine-carbon-fluorine bond angle is a smaller bond angle at 106.8 degrees, and the bromine-carbon-chlorine bond angle is a larger bond angle of 112.3 degrees. Explain the difference in bond angles using principles of atomic structure and VS-EPR theory. So I have to talk about a greater repulsion between the atoms of bromine and chlorine. So I said the atoms of chlorine and bromine have larger radii than that of the fluorine atoms. And so because of the larger atomic radii, there's greater repulsion between the electron clouds of Cl and Br, and that results in a greater bromine-carbon-chlorine bond angle. So that would be my answers to points 1 and point 2. Let's move on to our next part of this question involving intermolecular forces. It says, clearly identify all of the intermolecular forces in pure CBr4 liquid, which is on the left, and pure CBr-ClF2 liquid on the right. Well, they both are going to experience London dispersion forces, but one of them is nonpolar, and then the other is polar. So the CBr4 is a nonpolar molecule and can only experience London dispersion forces, but the CBr-ClF2 molecule is classified as polar. So it experiences a combination of London dispersion forces and dipole-dipole attractions. So that's my third point in this question. And then finally, for the fourth point, we can see a difference in boiling points. So in terms of the relative strengths of all of the intermolecular forces, explain why the pure CBr4 liquid sample has a higher boiling point than the pure CBr-ClF2 liquid sample. So what I'm doing is talking about stronger attractive forces or intermolecular forces for the substance that has the higher boiling point. So I said the following. Due to the greater polarizability of the electron cloud of CbR4, the London dispersion forces present in CbR4 liquid are stronger than the combined intermolecular forces in CbRClF2 liquid. Thus, the boiling point of CbR4 liquid is higher than that of the CbRClF2 liquid. So these are all 4 points of question 5. So now let's go ahead and move on to question 6, which is also a 4-point question. In question 6, it says a student performs a spectrophotometry experiment with solutions of vanadium 2+ ions and produces the calibration curve shown in figure 1 by measuring the absorbance of several solutions of known concentration. Now, the first part of the question, part A, says the student measures an absorbance of 0.32 for a vanadium ion solution, and then the concentration of the vanadium ions in the solution is represented by the particle diagram in the circle in figure 2. Now, I can see 8 particles, or vanadium 2+ ions, in figure 2, and the absorbance is 0.32 for that solution. In figure 3, we have to draw the correct number of vanadium 2+ ions to represent the concentration of a solution with an absorbance of 0.08. So we have to recognize that a lower absorbance means a lower concentration. Absorbance is directly proportional to concentration. So if we have half the concentration, that would be half the absorbance. Well, this is actually less than half. 0.08 divided by 0.32, that's actually 1/4 as much. And if it's 1/4 as much for the absorbance, it's going to be 1/4 as much for the concentration. So if I have 8 particles in figure 2, I have to draw 1/4 of that concentration. 1/4 of 8 would be 2 particles. So the correct answer to part A is to show a concentration that is 1/4 as much, and that would be only 2 particles in that diagram. So that's the first point. Now on to the second point in this question. The absorbance of a diluted solution is 0.22. Let's go find 0.22 on the y-axis in this diagram, and then we can figure out the molarity or the concentration of the vanadium 2+ ions. So 0.22, I trace that over to the line, I go straight down to the x-axis, and it's exactly halfway between 0.05 and 0.06 moles per liter. So my answer for the second point would be the molarity of that solution, that diluted solution, would be 0.055 molar. Now, it said in this experiment that the student took 3 milliliters of a more concentrated solution and then diluted it to a volume of 25 milliliters in a volumetric flask. So the next part of this question is to actually determine the molarity of that original undiluted solution. So if I'm going to use M1V1 equals M2V2, which is the dilution equation, the original molarity is a number that I don't know. The original volume of that more concentrated solution is 3 milliliters. The molarity of the diluted solution we just determined to be 0.055 molar, and the final volume in that volumetric flask was 25 milliliters. So my M1 is, I don't know yet. My V1 is 3 milliliters or 0.003 liters. My M2 is the value that I had determined from the diagram or the graph, and that was 0.055 molar. And again, my volume of that diluted solution was 25 milliliters or 0.025 liters. So I'm solving for M1. I've got M2 times V2 divided by V1. And my answer for the third point of this question would be 0.46 molar. That is the molarity of the original undiluted solution. Now, our last point in this question has to do with an experimental error. The concentration of the vanadium 2+ ions that were calculated in part B, II, is actually lower than the actual concentration of the undiluted solution. And the student claims that the reason that the calculated concentration is too low is because during the dilution step, as they were using that volumetric flask, the final level of the solution in that volumetric flask was actually higher than the mark on that flask. Do you agree or disagree? Justify your answer. So would this error cause the concentration to be too low? And I said yes, I agree. If the final level of the solution in that volumetric flask was higher than the mark, then the total volume of the diluted solution would be greater than 25 milliliters. A larger volume would mean that the concentration of the vanadium 2+ ions in that diluted solution would be too low, resulting in a lower measured absorbance. Thus, the calculated value for the original undiluted solution's concentration would be lower than the actual value. So there are my explanations for all 4 points of question 6. Now it's time to move on to question 7, which is also a 4-point question. In question 7, it says that sodium metal reacts with oxygen gas according to equation 1. So we can see a balanced equation in which 4 moles of solid sodium react with 1 mole of oxygen gas to produce 2 moles of solid sodium oxide. And the delta H for that reaction is negative 828 kilojoules per mole of reaction. It says that standard enthalpies of formation are provided in table 1, but one of them is a question mark. So that's what we have to do in part A. Based on the information given, calculate the value of the standard enthalpy of formation for the solid sodium oxide. Show the work that leads to your answer. So it's going to be the delta H of the reaction is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. Now, the overall delta H is negative 828 kilojoules per mole of reaction. We have for the products, we have 2 moles of sodium oxide, but we don't know what that value is. And then for the reactants, we have 4 moles of sodium, but that's 0. And we have 1 mole of oxygen, but that's also 0. So our math is the following. Negative 828 is equal to 2 times a number we don't know. And so that number, the enthalpy of formation for sodium oxide, is equal to negative 828 divided by 2, and the units are kilojoules per mole. So when I do that math, I get negative 414 kilojoules per mole, and that is the standard enthalpy of formation for solid sodium oxide. So that's the first point of question 7. Now moving on to the next point, it says an 18.4 gram sample of solid sodium reacts with 12.8 gram of oxygen gas according to equation 1. So we have 2 different reactants. Calculate the total amount of heat in kilojoules released during this process. So because we have 2 different reactants and we don't know which one will be the limiting reactant and which one will be the excess reactant, I'm going to consider that point 2 of this question is to identify the limiting reactant. So first I will go from grams to moles. Then I will use 1 mole of reaction for every 4 moles of sodium. And then 828 kilojoules of energy is released for every 1 mole of reaction. Now that number that I just calculated may or may not be coming from the limiting reactant. So I'm going to repeat that process. I did it with 18.4 grams of sodium. Now I'm going to repeat the process with 12.8 grams of oxygen gas. So grams to moles. Now I have 1 mole of reaction for every 1 mole of oxygen from the balanced equation. And then again, 828 kilojoules of heat released for every 1 mole of reaction. And what I discover is I get a different number for kilojoules of heat released. So identifying the amount of heat released is point 3. Identifying which substance is the limiting reactant is point 2, in my opinion. So it turns out that sodium is the limiting reactant because it produces a smaller amount of heat from our stoichiometry calculations. So again, the identity of sodium as the limiting reactant is what I'm calling point 2. And then for point 3, it is determining that 166 kilojoules of heat is released. So again, I'm using a limiting reactant identification as 0.2, and then the actual value of heat in kilojoules is 0.3. All right, the last point of question 7 is coming up next. Lattice enthalpy can be defined as the energy required to separate an ionic crystal into gaseous ions. Now we have rubidium oxide and sodium oxide. They have similar structures, but they have different lattice enthalpies. Using Coulomb's law, explain why the lattice enthalpy of rubidium oxide is smaller than that of sodium oxide. Now this is not about the magnitude of charge, because the positive ions in these two compounds are both +1. It's about the size of the ions. So what I said was, the rubidium ion is larger in size than the sodium ion. So the distance between the rubidium ion and the oxide ion in the crystal lattice, or the solid rubidium oxide, is a greater distance. So greater than the distance between the sodium ion and the oxide ion. So as the distance between the ions increases, Coulombic attraction decreases, resulting in a smaller value for lattice enthalpy. So that was my answer for the last point of question 7. Okay, well now this is the end of the video. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side during this school year, as you did your best to strive toward that 5. And I hope that when the AP scores come out in July, that you will be happy with your score on the AP Chemistry exam. Thanks for watching.